In this video, we're going to talk about confidence intervals, and in particular, finding a confidence interval for a population proportion. So you might hear a statistic like 22% of Americans use Twitter. And that's a useful statistic, but it's missing some information. So, how good is this 22%? Clearly, Pew Research didn't poll every American. They didn't talk to me, so they didn't ask everybody to find the statistics. So how good is it? How many people were surveyed? How close do they know their estimate to be? How certain are they that they are in a certain range of the true population proportion as opposed to this sample proportion 22% or 0.22? So if you read the specifics of a study or an experiment, instead of just seeing that 22%, you'll see something like this, a 95% confidence interval, such as that. And so this is, we might say things like, based on the sample size, we are 95% confident that the interval from 0.19 to 0.25 contains the true proportion of Americans that use Twitter. And so that confidence interval, it's 0.22 plus a margin of error and 0.22 minus a margin of error. The margin of error in this case would be 3% or 0.03. The sample proportion, that is whatever proportion of people ended up saying yes to this survey that they initially did. That's 0.22 or 22%. It's also called the point estimate, and it's denoted P with a little hat on top of it, because the true proportion that we don't know, the real proportion of Americans that use Twitter, is denoted as just P. This is a confidence interval of P hat minus the margin of error to P hat plus the margin of error. And 95% in this case would be the confidence level. And the confidence level can change. We can look for a confidence level typically of either 90%, 95%, or 99%. So if you're reading the results of a study or survey or medical literature, like for example, what proportion of people does a vaccine work for, or what proportion of time does a vaccine work, for example, then these would all have not just the initial, 80% or whatever, but also a margin of error and a confidence interval with a particular level of confidence, typically 90, 95, or 99%. So let's talk about where all these values come from. How do we get that margin of error, etc.? And so we will always estimate population proportion for experiments with a binomial distribution. Remember that X is the number of successes in N trials, where each trial has probability of success P. So in our particular Twitter example, suppose that our sample size was 800 people. So we poll 800 people and ask if they use Twitter, and 176 of them say yes. Then our sample proportion is P hat equals 176 yeses over 800 people polled. So that 176 over 800, that turns out to be the decimal value 0.22. That P hat is our sample proportion. More generally, it's called the point estimate. And the point estimate is always your best estimate of the true population parameter that you're trying to estimate. In this case, we are trying to estimate P, the true population proportion of Americans that use Twitter. So we're trying to estimate P. We found the sample proportion P hat is 176 over 800, or 0.22. So according to the central limit theorem, a binomial distribution with N trials will approach a normal distribution. Why is that true? So remember that the central limit theorem is about sample means and says that for size n at least 30, sample means for samples of size n will approach a normal distribution, or the distribution of the sample means is normally distributed. So a sample proportion we really can think of as a sample mean, where each yes is a 1 and each no is a 0. So if I've got a bunch of ones and I'm adding them together, 1 plus 1 plus 1 plus 1, blah, 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 and that's all my yeses, plus 0 plus 0 plus 0, that's all my no's, and I'm dividing by n the number of people in my survey, or, the number of times that medicine worked or didn't, or whatever, that sample proportion really is a mean or an average of a bunch of ones and zeros. That is a sample mean. So that p hat is a sample mean, and therefore these sample means will have a normal distribution according to the central limit theorem. So we can use the normal distribution to model this, which is really useful. What is the mean of our normal distribution in this case? It is p hat, that is our mean, so it will be normally distributed with a mean of our sample mean p hat. Okay, so we want to be 95% confident that the true value of p, the true population proportion, is in some range from p hat minus e to p hat plus e. So we want to find some margin of error e such that p hat plus e to p hat minus e contains 95% of all the sample proportions that we will ever take. So we want to find the margin of error such that this is true, such that p hat minus e to p hat plus e on the normal distribution contains 95% of the data values. So what is e? Well, we do know that z is equal to x minus mu over the standard deviation. This might seem like a digression, but remember this is back to z-scores. A z-score is the data value minus the mean divided by the standard deviation. What is that in this case? Well, that's x minus p hat over the standard deviation. And now let's try to solve for x. We're trying to solve for x. What position contains this data that we're interested in? So we're going to solve for x, and we're going to multiply both sides of this equation by sigma, the standard deviation. So z times sigma is equal to x minus p hat. And that means that if we're solving for x, p hat plus z sigma is equal to x. So this is x, and that means that p hat plus e is equal to x. That means e, our margin of error, is z, the z-score that separates 95% of the data from the other data in the tails, times sigma, the standard deviation for this binomial distribution samples from a binomial random variable with n trials. So that means that our margin of error e is given by z times sigma, where sigma, the standard deviation for a binomial random variable, where we're talking about samples of size n, this is going to be the square root of p hat, the sample proportion, times 1 minus p hat, divided by n, the sample size. So that is always going to be the standard deviation for how these binomial random variables are randomly distributed. So that is our standard deviation. Now what about z? So we're looking for the value that separates the 95% in this case of the data in the middle from the rest. And so for us, we're looking for the z-score that does that, such that 95% of the data is in between z and negative z on the standard normal distribution. So if there is 95% of the data in the middle, then between the two tails, here and here, there's got to be 5% altogether. So 5% of the data in the two tails together, or 0.025 in each tail, 0.025 in each tail. So what is this z-score? It is separating the top 0.025 from the remaining 0.975 to the left. So there's this 0.975 to the left of that value for z. So we can now read the table backwards. We can read the z-score table backwards to find the z-score that goes with 0.975. So let's look for, in the middle, the probability 0.975, and here it is. So 0.975, what z-score does that go with? That goes with a z-score of 1.9, and then up at the top, 1.96. So 1.96. Now you will not have to do this every time. So the critical values that we're going to use, these common confidence levels that we're using. So right now we're looking at a 0.95 or a 95% confidence level. That goes with a z-score or a critical value of 1.96. So in our case, z is 1.96. You could get this for any confidence level. You know, if you wanted a 98% confidence level or whatever, you could find that by reading this table backwards. But we're going to just be using these same most common confidence levels each time. So instead of going through all of that, you can just use this part of the table or those three values to say this 1.96 is the z-score that goes with a confidence level of 95%. Or that is 1.96 is the z-score such that 1.96, 95% of the data in the standard normal distribution is between negative 1.96 and positive 1.96. All right, we now have all the pieces and the theory that we need to construct a confidence interval. So suppose that we poll 800 people and ask if they use Twitter, and 176 of them say yes. Construct a 95% confidence interval for the true proportion of people who use Twitter. All right, so we're going to construct a confidence interval of the form p hat minus e to p hat plus e, where p hat is our sample proportion or our point estimate, and that is the number of people who said yes divided by the total number of people we polled. So in this case, that's 176 out of 800, or 0.22. We need then to find our margin. So this was the sample proportion. It's also called more generally the point estimate, the best estimate that we have of the true, in this case, population proportion. All right, so we also need to find E, that's the margin of error, and we found out that E is equal to Z times sigma, where sigma is the standard deviation. For these binomial distributions, it's always going to be given by this formula. Sigma is the square root of p hat, the sample proportion, times 1 minus p hat divided by by the sample size, and that whole thing is square rooted. So let's calculate this in this case. That means that sigma is equal to the square root of 0.22 times 1 minus 0.2, 1 minus 0.22, that's 0.78, divided by the number of people in the sample, that was 800. And then we can calculate that value, and we'll find that that is 0.0146. So that is sigma. We still need to find Z, the Z-score that separates the, in this case, 95% in the middle from the rest of the data, and that's based on the confidence level, 0.95. Like I said, we'll only ever be using 3 different confidence levels, so 0.95 goes with 1.96, so that means that Z is 1.96. So E is just multiplying those two values together, Z times sigma, that's 1.96 times 0.0146. And when we multiply those two values together, we'll get 0.0286, or maybe we'll use 0.029. Let's round to 3 decimal places this time. So that means that now our confidence interval is, again, the sample proportion minus the margin of error to the sample proportion plus the margin of error. So that's 0.22 minus 0.029 to 0.22 plus 0.029. And so our confidence interval is 0.191 up to 0.249. So that is our confidence interval. And what that confidence interval means is that if we did these sample proportions and we took them over and over and over and over and over again, 95% would fall in the interval between 0.191 and 0.249. 95% of the sample proportions of size 800 that we took would fall within that interval. That's what we mean by a confidence interval of 95%.